So I want to talk about something I've been working on for about a year, trying to connect some ideas which in type theory and zero knowledge, which haven't really been connected in the past and I think should be connected. But I'll emphasize this is still very much work in progress, and so I'd like to have your feedback, and I hope this is the beginning of a dialogue. So I'm going to begin by saying what I mean by type theory. And I mean, so when I talk about type theory, I'm not talking about a specific formal system, but a certain ideas and particularly a certain constructive mindset in logic, which goes back to the ideas of Brouwer in the early 20th century. And one of the, perhaps the most defining characteristic of so-called constructive logic is this existence property. So you can state it that if it's a theorem that exists x phi of x for some predicate phi, then that implies that it's also a theorem that phi of t for some particular individual t. Now, there's another way of stating the existence property which perhaps gets the point across better. And it's that if you have a closed proof of an existential statement, you can actually transform it into a proof which you can see it as which ends in the existential introduction rule, but applied to a particular t. And for people who think about the computational content of proofs, you tend to read proofs bottom up, starting from the last rule. So you can see this as saying that any proof of an existential statement begins by, you can transform it into a proof that begins by stating the witness. Now, finally, I want to say one more thing because it's going to come back later on, and that's the connection between classical logic and constructive logic. So when the classical logician makes an existential statement like exists x phi of x, well, there's the constructivist has different ways of interpreting. They might interpret it as a double negation of exists x phi of x, or that it's not true that for all x, not phi of x, or there's different ways of interpreting it. And these are all these so-called double negation interpretations. They go back to again, the early 20th century, Kolmogorov, Gödel, Gensen. They show different ways of embedding classical logic into intuitionistic logic. And there's different ways of doing this, but the important point is that when you do this, you usually lose the existence property. It's not true for one of these formulas on the right that a closed proof will necessarily begin by introducing a witness. Okay, so that's type theory in 3 slides. Now I want to talk about zero knowledge. So, okay, here's the intuition. Prover knows a valuable secret. So they claim to know an x such that phi of x. But verifier is skeptical. So they go and they play a certain protocol. At the end of this protocol, verifier is convinced that prover really does know such an x, and hence that there exists an x such that phi of x, because if prover knows an x such that phi of x, there must exist an x such that phi of x. But verifier has no idea of what the x actually is. So, okay, that's the idea. Now, if you think about what I just told you, you might see why somebody with a background in type theory or constructive logic will look at this and they won't know exactly what to make of it, because how can it be that you have how can you know that exists x phi of x without knowing the witness? Okay, so that's one reason why I'm interested in this. Now, okay, so what's an example? So there's this protocol for zero knowledge, which goes back to Manuel Blum. You can give a zero knowledge protocol for the problem of graph Hamiltonicity. So here we have a graph, and it's Hamiltonian. And okay, so I guess these are going to stay cut off, but okay. So this is the prover's knowledge. They know a path. And they want to convince the verifier that this graph really does have a Hamiltonian cycle, but without revealing what the cycle is. So here on one slide is Manuel Blum's protocol. So if you haven't seen it before and you don't have very good vision, you're probably not going to understand all the details. But basically, the idea is that we have this property of being a Hamiltonian cycle in a graph, and it's invariant under isomorphism, graph isomorphism. So the prover takes their knowledge and they split it up into, they permute the graph, and so now their knowledge becomes the knowledge of a permuted graph and a Hamiltonian cycle in the permuted graph. And then they commit to this knowledge. Then the verifier, they're allowed to ask them one of two questions, either to see a Hamiltonian cycle in the permuted graph or to see that to see the isomorphism. Okay. So that's the idea, and the idea is that the verifier, after repeating this protocol many times, the verifier becomes convinced that the graph really does have a Hamiltonian cycle, but they don't have any idea of what it is. Okay, so I've explained type theory and zero knowledge very quickly. Now let me just explain what I mean by hope. And by hope, of course, I mean higher order programming with effects. And higher order programming means that we talk about code being passed as data. And effects is a term from theory of programming languages and refers to a certain class of phenomena, things like input-output, non-determinism, exceptions, and probabilistic computation. Let me say, talk just a tiny bit about higher order programming. And the approach I'm taking has to do with this old idea from programming semantics called continuations and continuation passing style. It's a very simple idea. A continuation, the idea is it's a function from values to final results of a computation. So K is a continuation. And in a certain sense, you can see this as the propositions as types view of negation. So a continuation, in a certain sense, is a generalized refutation. If you view the final answers as a sort of contradiction. And then the idea is that by building these up, by passing continuations to continuations to continuations, so sort of building negations of negations of negations, you can encode different complicated control structures. Now, effects, I'll just say quickly what the idea is. Why it was seen as an issue in semantics. So suppose you have a programming language and you have a probabilistic operation. So say unif of n samples to return an integer random uniformly drawn from 0 through n. So now you might have some simple equation like x plus x is equal to 2 times x, and you can substitute for the variable. So you can replace x by, say, 3 times 4, and the equation is still true. But what happens if you replace it by unif of 2? Does that equation still make sense? And it doesn't really. I mean, if you think about it, the left-hand side, you have to try to make sense of it, but intuitively, the left-hand side is equal to 0 with probability 1/9, and the right-hand side with probability 1/3. So, okay, so one approach to dealing with this semantic problem of effects is to treat effects as modalities. So the idea, you could imagine distinguishing between a pure term, a pure proof of A, and effectful terms, or if you're thinking logically, sort of pseudo-proofs. So this notation, I'm using bracket D of A and bracket S of A. You can just imagine it as talking about probabilistic computation. So bracket D of A standing for a term which is computing in A but might have probabilistic effects. And a bracket S of A is a term computing in A but which might also have probabilistic effects and exceptions. So I'm not going to say more about this, but there's a way of making sense of this in type theory using ideas from algebra. You can think of D, this effect D, as an algebraic theory, so the theory of finite probability distributions, you can think of S as a theory of finite sub-probability distributions. And you can think of this bracket D of A as building a free algebra over A. So, okay. Now, so how much time do I have? 3 minutes. Okay, so what is the hope? Should I include the disclaimer? Okay, I'll include the background disclaimer. So I'll read it. The type theory described here, which maybe I won't have time to describe completely, but describe an ongoing development in AGDA, which is experimental dependently typed programming language. In this setting, the theorems we prove can be directly applied to executable programs. So we can even try to confirm or refute conjectures by running these programs, by testing them. But okay, an emphasis here is this is ongoing work. And the first sketch of types, which hopefully I'll have time to describe to you, will be an inadequate encoding of this protocol. But then I'm going to replace it by so-called two-dimensional conjecture I have about inadequate encoding. So, okay, so I'm starting to describe some type theory for you. So the idea we start with, I'll call it a knowledge family. So a certain predicate phi over some type A, and you can think of, in this case, you fix some graph G, and A is the type of paths, and phi of x is the predicate that x is a Hamiltonian cycle in G. And in this case, we know that the phi is decidable. In fact, it's efficiently decidable. And A, so in this case, the paths is a isomorphic to a finite set. Okay. So let me move on. So now the idea is we can define a type of provers and a type of verifiers for this problem. So then we can talk about different provers and different verifiers living in these types. And we have a way of combining a prover and a verifier to get a result, in this case, an answer, a probabilistic Boolean, a distribution over Boolean answers. Now, the statement that we have a zero-knowledge proof system, or technically a zero-knowledge proof of knowledge, says that there exists a particular prover. And now I'm switching to the sigma and pi notation just to be clear. So the notation from dependent type theory. So there exists a prover, P, which is indexed by witnesses, and there exists a verifier V such that P has the property of being zero knowledge, which I'll describe shortly, and V has the property of being knowledge validating. This idea of, okay, zero knowledge prover, knowledge validating verifier comes from complexity theory and this idea of zero knowledge. Here I'm trying to capture that in type theory. And maybe, okay, we don't have time to go through the details of this definition. In order to state it, I have to talk about probabilistic computation. Okay, maybe let me just say quickly, the basic idea of zero knowledge is that you can define a simulator which, given access to an arbitrary verifier, simulates its interaction with the honest prover given access to the witness. The idea is that you show zero knowledge in terms of simulation. I mean, effectively, it says that any verifier doesn't get any information from the prover because they could have just simulated it by themselves. And knowledge validation says that there exists an E, and this is typically called the knowledge extractor, which, given a prover, tries to extract a witness. Given access to a prover, tries to extract a witness to the existential statement. And assuming that this prover beat the verifier in the protocol with sufficiently high probability, then with high probability you can extract a witness. So maybe I will just show this slide and then state the problems with it. So what is how do you actually define the protocol? And the idea is that we can do it by using this idea of continuation passing. So the types of provers and verifiers correspond to sort of nested negations. How much time do I have? Like negative... Okay. So these are logical formulas, but they encode this protocol that for specific to the problem of Hamiltonian cycle, where the prover begins by probabilistically computing an initial move, which is going to be a commitment to an isomorphic graph and a cycle in that isomorphic graph. Then the verifier responds by making a request, either see the isomorphism or the cycle, and then the prover responds to that request. And this type, which is these nested negations, can be seen as encoding that idea. But there is a problem. So we can write the honest prover and the honest verifier with that type. But there's a problem which is an instance of this general idea of nonlinear continuation passing. The idea is that this type is a bit too general. It allows certain behaviors which seem to violate the protocol. So like, for example, a verifier might restart the prover. They might call them twice. First, they ask for the isomorphism. Then they ask for the cycle. That way, they can recover the cycle in the original graph. Or the prover might just abort. They might not respond to the verifier's request. And so, okay, so I mean, there's an interesting connection to the fact that these bad behaviors, this bad verifier, you can see it as actually being exactly what you use to write the knowledge extractor. And this bad prover is exactly what you need to write the zero knowledge simulator. Okay, so I'll just state the provisional solution I have, which corresponds to trying to generalize these verifier and prover types. Rather than having just a single type, it's really a family of types which have some indexing. And this corresponds to an idea of taking a two-dimensional view of these types, so interpreting verifiers and provers as pre-sheaves formally, and defining negation as a natural transformation rather than just a function. So I don't have time to explain this idea, but and it's still a conjecture. It's still a conjecture that this is the right thing to do. But it seems to rule out these nonlinear behaviors, but still let you write things like the simulator and the extractor. I'm still working on the proofs that these actually satisfy the zero knowledge and knowledge validity properties. But OK, with minus 5 minutes.
Okay, thank you very much. Questions? Yeah.
So, zero knowledge is one of the most complicated cryptographic protocols. Did you try putting in type theory some of the very simple cryptographic protocols, like passing a coin into a well, or doing just a commitment scheme with a sub-protocol?
Right. Well,
before doing this.
I mean, so about the commitment scheme, that's one question I have about how to talk about that. I don't really have a good way of talking about that here. I mean, it's in the encoding. I assume a commitment protocol, but I don't try to analyze it or to implement.
You assume some black boxes
Yeah.
that
Yeah.
you cannot implement it.
Yeah. Yes.
Did anybody do any work about putting any type of cryptography into type theory?
I mean, there's been sort of one of the.
Just public key encryption.
Yeah.
Right?
one of the ways I got into this was this work on formal verification of cryptographic protocols within type theory. So the idea of so languages like Coq, proof assistants, you can use to do lots of things, formal verification. And so there's this work, it's called the 30 Crypt project, where they did a lot of work of verifying cryptographic protocols within dependent type theory. But it's not really, there isn't much like semantic analysis. So it's more, you encode these protocols the way you typically would in informal mathematics. You might axiomatize some programs and make a logic about it and then try to do these proofs. But there isn't really trying to connect these ideas to logical ideas.
Okay, so, yeah.
You were referring to Blum at the beginning.
Yeah.
And as I understand, Blum did not give a vote, but some thing explicit was in fact of reasonable length to be actually computed. It was
Yes.
all theoretically computed.
Yes.
And for those questions of cryptography or
Yes.
whether it's crucial to take into account the
Yes.
length of computation. So
Yes.
does that theory have anything to tell about length of computation?
Right. So, I mean, let me maybe just show one slide. So, for example, or how about this? So, I mean, here I'm proving a statement which, okay, I can show a simulator which works for any verifier. The types themselves don't say, they leave out the complexity. So that's something which is missing from type theory. You don't have a way of expressing these complexity assumptions. That's something which is an open question, which is an important question. On the other hand, it's something which isn't in the logic, but we can still, in the same way we always do, we can look at the proofs themselves, we can look at the programs that we write, and we can say, here I'm giving a simulator, and it's probabilistic polynomial time. I mean, we can. It's something which is in the meta. Externally, I can look at the proof. I can reason about it.